Okay, let's see if we can tackle this problem. Let's calculate the wavelength of light absorbed when the hydrogen atom undergoes a transition from n equals 1 to n equals 3. Okay, so when we have these transitions in the hydrogen atom, we know that we can use this equation right here, where NF is the final n, principal quantum number, and n initial is where do we start from. In this case, I say n equals 1. So we can use this to get the energy, and once I have that energy, I can then use that to calculate several things. I have a little error there, so that's E equals h nu. The nu is missing. And then E also equals h, which is Planck's constant, times c divided by lambda. That's what that should have said. Okay, so once I have the energy, which I can get from here, then I can use that to calculate the wavelength. And it looks like I can probably use this equation right here, okay, to end up getting the wavelength of that. So let's go ahead and do this. So let's set it up. So we have the change in energy of that transition is going to equal minus 2.18 times 10 to the minus 18th joules times this right here, which is going to be 1 over 3 squared. The 3 comes because that's my final transition, and when when a hydrogen atom absorbs a photon, then that goes from a lower energy state to a higher energy state. So that's going to be 1 over 3 squared minus 1 over 1 squared. And then when I do that, I'm going to go ahead and do that inequality right there. I end up with 1.94 times 10 to the minus 18th joules. That is the energy from there. And it's positive in this case because we know that when energy comes into a system, we already know that from our thermodynamics, then that is going to be a positive. It's going to be a positive number. And then it's also just kind of important, it's not crucial for this, to know that that change in energy is going to equal the absolute value of this change in energy. That the energy that I'm concerned with that photon. So even if this did come out to be a negative number, meaning that the system was then giving off, or in this case emitting light, that helps me then to deal with any negative value. Just know that that energy, when we move that over into these other equations, is going to be a positive value. Okay, so now remember that the sign, either minus or negative, really has to do with the movement of energy, not necessarily the magnitude of the quantity. And so once I have this energy, now I can use that, and I can use those equations and say that energy equals Planck's constant times the speed of light divided by the wavelength. I just calculated this. It's this number right here. And I know h, that's a constant, c is a constant. And so now I can rearrange this equation to say that lambda equals hc divided by the energy. So now I can just plug in the numbers. Planck's constant is 6.626 times 10 to the minus 34th. That will be given to you on your test. Times the speed of light, which will also be given, 3.00 times 10 to the 8th meters per second. And we're going to divide that by what we just calculated, this energy, which is 1.94 times 10 to the minus 18th joules. And so let's go ahead and see if we can get that wavelength. So let's go 6.626 times 10 to the minus 34th times the speed of light, 3.00 times 10 to the 8th, and then we're going to finally divide that by 1.94 times 10 to the minus 18th, and what comes out of this in meters is going to be 1.02 times 10 to the minus 7th meters, and if I want that in nanometers, then that is going to be 102 nanometers. Okay, so these problems are actually really doable, and you'll probably get a two-parter like this where you have to calculate the energy using this equation. So when you start seeing transitions moving or transitions falling from, maybe the problem will say it emits light, meaning we go from n equals 4 to an n equals 2. Make sure you set up your problem right. That n equals 2 is your final, so that's actually going to go right there. N equals 4 is your initial, if that's the problem I give you, so that's going to go over there. You're going to calculate an energy. Once you get that energy, you can calculate the frequency. You can calculate the wavelength using the equations that we should already know. That is, E equals Planck's constant h times nu, or E equals hc divided by lambda, where c is the speed of light, lambda is the wavelength, h is Planck's constant. You might also need to throw this intermediary in there sometimes. C, the speed of light, equals lambda nu. Don't be afraid of problems like this. Get the energy. Then use that energy to calculate wavelength or frequency given these problems that we already know.